But enough. I'll show you a better way of solving the diffusion equation, called the Crank-Nicolson's method. Again. Crank. Idea is fairly simple. You basically average two different time steps. Again, equation b alpha ux x, but we will average steps here. J plus 1 I j t equals half kappa make it more explicit 2 j j 1. So the method we had, well, last lecture, that was a explicit method. Whereas this going to be explicit. J plus 1 on the left side, J plus 1 right hand side. And this d squared, that's just the differentiation operator. We'll be using the central one again. And 2 x squared I minus 1 j minus j minus I 1 j plus I minus 1 j plus 1 I j 1 I minus 1 j 1. So, and then if we introduce r as kappa t, so basically this delta t here, multiply both sides, x, and we can save some chalk. We can rewrite this equation as minus r I 1 1 r 1 r plus 1 1. Okay, so we got them on the left hand side, all the time step j minus r r plus 1. Okay. Is that too small? Bit? Okay. Double check all of the i's and j's. So on the left hand side we have all of the j plus 1, then I minus 1, I plus 1. On the right hand side, all the j's are just j's. And we have first I minus 1, just I, and I plus 1. Okay, so we can rewrite this as a system of equations or matrices. 1 plus r, then just zeros, r. You see in the first equation here, this r disappears because that's from boundary condition. And implicitly now I'm using just zeros as boundary conditions. That's easier. We come back to boundary conditions in a while. 1 plus 2r minus r plus 2r und weiter r plus r, and in the end r 1 plus r. Then we have all of these u's. 0, j, 1, 1, j, 1, n, j. That's the left-hand side. Right-hand side, you haven't already guessed. 1 minus 2 r, r, 1 minus r, and I'm pirate. 3, r, 1 minus 2 r, yar, and 0, j, 1, j, j. So here we have matrix system of all this first one, A, second one, B. We have A being U as a vector. This one equals B, J. So, and again, themselves. And we'll look like this. T, J, 1, J, X, 1, X, I, and X, 1. So here we have more information. Yeah. And also we can show that the local truncation error for this method equal to P big O delta T squared plus big O of delta X squared. So Crank-Nicolson is second order in time and second order space. So, caveats. So intuitively, I hope you well, not hope, but intuitively you might think that this is more complex to solve than the explicit method I showed you last lecture. But due to these tri-diagonal bands, so it's a very easy structure on it. And one band here, and you have one there, one there. So it is a very sparse matrix, and it's actually a lot easier to construct this matrix than the one we had, well, last week. Yeah, with the Laplace equation. Though this is just 2D. Anyway, due to these tri-diagonal bands, you can assume, or actually in this case, depending on the R's, it is positive or negative definite matrix, meaning that it is very easy to solve with either the successive over relaxation or conjugate gradients. And in my opinion, conjugate gradients would be best here. So you can actually, even though it's matrices, it can be solved in linear time. So if n is the amount of grid points you have, you can solve it in big O n time, where n is the amount of grid points. So it's a linearly computationally complex increasing problem. Usually you want this n to be as low as possible, and big O n is very good. That is very good. Usually, no. It's a kind of a same concept as with the accuracy, but here here it means how quick the computational complexity increases. So if you have big O of n squared, it means that for every time you double your amount of data, you will quadruple your computational complexity, which is not good for huge systems. You choose your n. That is the amount of points, grid points, in this case. You also choose the delta x and the delta t. Those are the grid spacing. The big N here is how many points you have total. So since this is a linear problem, or it can be solved in linear time, and, well, this n is just linear, it's just n to the power of 1, then it's not that computationally complex to solve, even though you have two matrices to solve here. And again, going back to stability, I can just mention that this Crank-Nicolson is unconditionally stable. So you can pick and choose these delta t's and delta x's as you want. And you won't have this problem with it just exploding, just showing garbage. So it's a much better method. So the explicit method, that's also big O of n, meaning linear in time or linear complexity. So the complexity is the same in both methods, only this is a lot better. A lot better. And I'll just mention that for better accuracy, without proving anything, you can get a great accuracy by picking delta t approximately equal to delta x squared. Or low error, even though it's linear, second order in both time and space. Going through the math, you see that if you pick your time step to be approximately the square of the spatial steps, you will have the best results in this method. Questions? Oh. Okay. And up until now, we haven't really thought about boundary conditions. So implicitly, I've said that the boundary conditions are just 0 on both ends. Now we'll try to introduce boundary conditions. It won't really complicate matters that much, but it's more to write. Can I remove the matrices? Good. Now, of course, if you want to implement Crank-Nicolson, I urge you to use sparse matrices today with your Laplace, because then you don't have to store all of the zeros. Okay, so now we'll look at boundary conditions. Meaning that we will set 0 t kind of constants on the left-hand side and a t constant on the right-hand side. This is just an ampersand. At symbol or and symbol. Handwriting. It doesn't mean anything else than and. Will to write. Okay. Meaning that we have our grid here. So left hand side CL, right hand side R. All the points here. So in the explicit, this is fairly straightforward to implement. Meaning that on the explicit method, so the one I showed for the break, and for the left-hand side, I1 equals ij plus kappa t delta x squared 0 j one, yes, 1 j so, and here we don't know what this, well, we do know 0 L. And then you solve the rest. So that's fairly simple. On the right hand side, have n j plus 1 j kappa t delta x squared n minus 1 j minus j plus 1 j, and since this n plus 1 so-called out of bounds, this again start counting from 1 here. Here is number n, number 1, number 0, n plus 1. This point, so here R. On the Crank-Nicolson, it's different, but the same principles. Left side minus R 0 J plus 1 plus 2R J plus 1 R and 2 plus 1 R J plus J J. Again, we just insert for the boundary condition. L L and up with just putting all of the CLs on the left hand side plus 2R 1 J plus 1 R 2 1. And if you take a look at your notes and look at the matrix that was just here, you see that that was also how it started. 1 plus R, then minus R in the next element. This time we boundary condition 2R L plus R 1 J. Then similar with the right hand side. So it's similar, so if you give some details, give it this. I mean, this is just the equation, and you just change instead of the right, no, the left, you have to change this one to the TR, meaning you will end up with minus R U and minus 1 plus 1 plus R J plus 1 equals 2R R plus 1 minus 2R. No. It's R and J 1 plus 1 minus 2R and J. So you basically have same A matrix as 4. J plus 1 equals, well, just have the same B matrix, what you will change use. You are now to RCL is here. And again, if your boundary conditions are time dependent, it's not going to be complete. Then you need to make sure of the time. Just as a side note. Here I've assumed that the boundary conditions are time independent. Okay? It's the same with the stake, because the changing of temperature there isn't exactly time independent, because you do change the time at one point in time. You could also simulate it with the oven heating up itself. Then you also have a time dependent boundary condition. Then you need to make sure that on the left-hand side, you have the CL evaluated at time j plus 1, and at the right-hand side, you have the CL evaluated at time tj. So let me just finish this, and I'll finish that other thought. 2r 0 j plus r j. Then we begin per usual. J plus 1 minus 2r 1 j plus r e j. It's going to be 1 there, and 2 there, and 1. Notes are wrong. Ru minus 1 j plus 2ru plus r. This is your B. A. Can actually read that. So, back to what I was trying to say. That is, if this boundary condition here is time dependent, you have to make sure that you have value at both time steps. So then it's CL and TJ 1 plus, no, 2 now, R plus C of L evaluated time J. R. Just as a note, if you want to do it properly. Yeah, questions about this? No? Then we have a third way of solving this, and that is rewriting the PDE till a pair of ODEs. And this is called the method of lines. Basically, forming the PDE system of ODEs. Is basically for this equation, you want to find, you actually want to find this u of t. So that is going to be your variable, so to speak. So you are looking after, you're looking for the change instead of the actual, for instance, temperature. And yeah, I've set the constant to Martin. Include it, kappa xx. Forming from this PDE to an ODE t over x squared. Thing again. T I time t plus I plus 1 plus 1 t. So do you see the difference? Or is it the same for you? You basically want to solve for, instead of solving for u, you're solving for the u differentiated with respect to time. So this is what you're after. Change. Then you can update them. This. It is changing with time, but instead of finding the actual value of u, for instance, the temperature or the pressure, you want to solve it for the change in pressure or the change in temperature. You're trying to solve it as an ODE instead of a PD. And then you can update this u again. That's okay explanation? Meaning that you can throw whatever you want on this, as we had earlier. For instance, the Euler or Heinz method, or the Runge-Kutta, or 2, or 16, if you're feeling adventurous. So that is actually all I had for the diffusion equation. And I don't think we have enough time to start on the numerical solution for the wave equation. That's going to take more than 10 minutes to expand on. Yeah, no, we're going to do this next time. I can just show you an example, and then you can go 5 minutes early. So I can mention this as a side note to the project. So this is actually the wave equation being solved. A problem with solving this hyperbolic PDE, that is the boundary conditions. So if you pay attention here, either I send a signal from up here, then you get a reflection from the bottom here. So what I have done here is I've actually cheated. I have actually ignored the boundary conditions, which you also can do if you want. I actually do recommend you to ignore it. And that is something called absorbing boundary conditions. So what is happening here is that what I'm showing you is just part of a lot bigger thinking about it. So if you pay attention, there's a shot going off here, and then I get reflection from the bottom. So what's going on there? So you're starting here, sending the shockwave both up and down, but you only see this part. What is happening there is that the wave has time to actually go through the end here and reflect back up. But it stops here. And that doesn't really matter because also it's a lot colder up here. So the wave field has time to actually reflect from the boundary here, but it never appears at the top here. Same on the left-hand side, get a reflection going back again. But it never reaches the origin point. Why is that? Well, what I'm actually doing here is I'm running multiple simulations. I'm running one shot from this grid point, then the next grid point, and now you see it's all the way over there. So I'm collecting data from all of the different shots here. And I'm also recording the response at the top of this box. So as long as the false reflections does not reach back to the receivers, they don't really exist. You don't measure them, so they don't really matter. So that is why you can actually do this trick and not care about the boundary condition. Not really care about implementing something called perfectly matched layers, so PML, or ABC, which is absorbing boundary condition. I won't stop you in doing it, but it is a hassle to actually implement. And the vector is that this rectangle has 50 grid points down here and 100, just 100 here. But in order for it to not reflect back, I need to extend it by 100 on this side and 100 on this side, so I don't back. This is just cut out of the reel. I'll also give this on the project. So what's happening here is that you get some kind of response from the medium, and you are supposed to actually invert these waves and figure out what the medium is. And I've tested it, and it works. Yeah. Yes, the thing you're seeing here, there's a model behind this. And the thing is, I won't give you the model I'm using to generate the signal, but I will give you a starting model. And you should be able to recover parts of this true model, which is actually what you do in full waveform inversion. For instance, you can drill a test hole or something, and then you get the lithography of just this one section, but you don't know the details here and there without actually drilling. You have some layers. you won't be able to recover the layers that neatly, but there's kind of a full reservoir down there, which you should be able to recover. It's basically you have layer and then maybe one more layer, maybe you have something else inside here, and then you have a reservoir you want to recover from. And you can use whichever trick you want, try to actually figure out the model. Actually looking at the recordings also, if that helps you to construct one. But then you need to document what you're doing. And yes, I will give you this GIF if you want to study it. So yeah, any questions about that? Have any of you done full waveform inversion before? You know what it is? Have you done tomography? Yeah, this is similar.